Questions on the homework? What would you like to see explained or clarified? Yes, Taylor.
25.
25? You know what that is, or do I need to bust out my book here? I can get it, I got it here. So 25, if I can get to the right place, is... So we're trying to find domain and range, does that sound right, of y equals 1 over x squared plus 2? Or no, am I on the wrong page?
No, it's the one from number 3.
Number 3, okay, so the next page over,
It's on page
18, okay. Sorry about that. Okay, scratch that, 25. So 25, and we are on page 18. So it says a photocopy machine, okay, can reduce it, copies by 80%, and then you want A and B or just any one of those?
Both.
Both? Oh, wait, no. No, you're wrong. So we're going to reduce by 80% first. And then we want to know what percent enlargement do we need to get back to the original. So what percent enlargement to get back to where we were. So I'm going to do this like it's an equation. So we know that, we'll say, here's our original size. We're going to call that S. And we reduced it by 80%. By 80, reduced by 80% or to 80% of, not by, I'm going to say to 80% of its original. So that means that we took that original and we multiplied it by 0.8. You okay to that? Now what we want to know is what are we going to multiply it by to get back to that original. So I'm going to write it like it's an equation. Does that make sense? And then I'm going to solve it for this x, which is going to turn out to be a decimal that I'm going to then make into a percent. Okay? So I'm going to divide by the 0.8f. Ainsley, okay?
Yeah.
Okay, so that's going to divide out, doesn't really matter. So we have 1 over 0.8, which, of course, everybody knows is 1 over 4/5, which to divide by 4/5 is to multiply by the reciprocal. Of course, we know that's 1 1/4, or 1.25. Or what was the question we were asked? By what percent enlargement? So to make that a percent, we'll call it 125%. Kind of crazy, huh? Okay, do you want to try B? Estimate the number of times in succession that a page must be copied to make the final copy less than 15% of the original. So that's where we're going to multiply by 0.8 each time. Does that make sense? So what we want to do is take 0.8 to what power is going to be about 0.15. Is that okay? And I don't know, I guess we could take a logarithm, I guess, or it's almost as easy, I think, if you just get your calculator, you go 0.8 times 0.8 times 0.8 and just count how many you do until you can get close to 0.15. I mean, you can take a log of both sides, so we could, you know, it almost seems like overkill on this one. And we can bring our exponent out in front using our properties of logarithms. Is that okay? And then divide that over. I'm not even sure this is really what they wanted you to do, to be honest. I'm not sure. And It would be, you're looking for an integer, so this is gonna give you some messy decimal, but you just kind of pick the integer that is closest to, because that's gonna be how many times you would reduce it there. Okay, anything else?
Could you do 35, please?
35.
It's on page 19 as well.
Page 11, okay, so 35. So number 35. So we have a table, and it shows some values of a linear function f and an exponential function g. Find exact values, not decimal approximations, for each of the missing entries. Oh boy. So, let's see if I can do this. We have x, f of x, g of x. And the x values are 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. And the f is 10, question mark, 20, and then a couple of question marks. And the g is going to be 10, question mark, 20, and a couple of question marks. And so I guess we know that f is linear and g is exponential. Okay. Do you want to do both of them, or can I get away with one?
Could you just do the exponential, please?
Yeah, the exponential is the hard one, I think. So here you can find slope, because you have 0, 10, you even have the y-intercept, 0, 10, 220, you can give the slope, and you got y equals mx plus b. The exponential is tougher, because we're going to go y equals ab to the x. So we'll plug in these values. So I'm going to plug in 10 for the y and 0 for the x. This isn't going to be too bad, I guess. So b to the 0 is 1, so we know a is 10. Now we're going to go back to y equals ab to the x, but now we know what the dA is. And now we're going to plug these in. So we get 20 is 10b squared. Okay?
Yes, sir.
Divide by the 10. And we'll get b squared is 2, so b is going to be square root of 2. So we're going to get y equals 10 square root of 2 to the x.
Okay.
Now once you know this, you're just plugging these in. And did they ask for, I think they asked for exact values, 95 or? Find exact values. So you can't use your calculator. You're going to have to deal with the square root of 2 and raise it to those powers. You okay with that? You want to see one of those?
No, I'm good.
Okay, anybody? What else? Okay. Money's on. Do make sure you're doing this, you're getting your questions answered right away. Because we will be piling on stuff, which is going to make it critical that you stay caught up in understanding and work both. Okay, so this is 1.3, which is new functions from old. We're still in the review part of our class here, but we'll blaze into new stuff soon enough. So we have this long list of known graphs of functions. So these are ones that we've talked about in the past, and when I write these down, you should have like a mental picture that jumps into your head right away. If you do, it just makes your life much easier, and you can worry about other deeper concepts than just what in the world is the graph of, that can look like. So I'm not going to write all these, I'm not going to graph them all, but but we'll get kind of a laundry list. So certainly you should know what is y equals x, y equals the absolute value of x, y equals x to the second, y equals x to the third, y equals the square root of x, y equals the cube root of x, y equals 1 over x, y equals e to the x, y equals natural log of x, y equals sine of x, y equals cosine of x. And so really, when I say know the graph, it doesn't even have to be all that precise, but you should have a good feel for what that looks like anyway. So when you see a sine, sine x, you should know that it's going to do this kind of thing here. And that its maximum and minimum are going to be 1 and -1. And that it's going to have a period of 2 pi. Just kind of those basics there. And then the other stuff, we'll talk about, but that isn't really as important. Interestingly enough, as much time as we spent graphing sine, cosine, tangent, cosecant, cotangent, and secant last year, you won't be asked to do that on an AP exam. Now, you may need to know some basics about sine and cosine and tangent, but anything else that they are going to ask that you need a graph for, they'll put it in the graphing calculator active part of the test, and you'll be able to graph it on your calculator. Or they'll print it for you on the test and say, here is, f of x equals blah, 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 and they'll give it to you. So this is not a huge idea, but yet knowing some of these really is important and valuable. This one maybe we don't know as well, but remember this is going to look something like this. And so that's y equals 1 over x. Put that one down there. You know that because at 0 it's going to be undefined. That's the vertical asymptote at x equals 0. As x gets really, really big, 1 over something huge gets really close to 0. That gives you those horizontal asymptote of y equals 0. So we should know that. And then we ought to be able to do all that kind of stuff that we do in Algebra 2, but have an understanding of it. How you reflect, translate, stretch, shrink, that kind of stuff. So reflections, translations, stretches and shrinks. So still important, not to the degree that we did last year, but it's still foundational. So we need to know that. So we should, for example, see if we can find our way through this. 2 times, say, the square root of x minus 1 over 3 plus 4. See if we can get some cobwebs out for that one. So hopefully in our head anyway, we know that the square root of x, this is our parent function. It's the top half of a sideways parabola. So that's what we're starting with. Now we know that the x minus 1, the x plus 4, that's going to translate it to where? You don't have to worry about taking turns here. Just go ahead and blurt it out. So yeah, plus 4, plus 1. So the point that was at the origin is going to now be at 1, 4. Okay? Whew. A long summer. Okay, so far? The negative is going to do what? Flip it in the x. Now, so we're talking about something that's going to go down and to the right. Now, normally, a square root you get 1 point, you're gonna go over 1, up 1. But because of the 2 and the 3, what is the 2 gonna do? Stretch or shrink in which direction? Stretch in the y direction. So instead of going, because it's reflected, instead of going down 1, we're going to go down 2. And the over 3 is going to be stretch or shrink. Stretch in the x direction. So this is the one that goes kind of counterintuitive against what you would think. So we're going to go down 2 and over 3, and that's going to be a second point. You with me? It's got coordinates 1, 2, 3, 4. And did I leave it up at 2? And that is going to be our curve. Okay, not much of that in AP Calc. That's okay, you won't see some. Okay, so let's talk about composite functions. So composite functions, we have a more familiar notation and a maybe not so familiar notation. So we usually write it as f of g of x, f composed with g of x. This can also be written as f with this kind of funny little open circle g of x, which a lot of Mr. Hogshead students like to call fog of x. Of course, we know better, that's f composed with g of x. Okay. And then also g of f of x, which a lot of Mr. Hogshead students refer to as goth of x. Ainsley, we okay?
Yeah, my eyesight's just not great.
Oh. You might want to pick a different spot next time, because I'm going to be on this board the whole time.
No, it's okay. My classes are coming in like a few days.
So you say your binoculars are coming soon?
Yeah.
Good, good, okay. Okay, so for example, f of x is equal to 3x minus 2g of x is e to the x. So we can write f composed with g of x, f composed with g of x. So remember, you're going to put x into g and then g of x into f is the way you do that, kind of right to left. So when you put all of g in for f, you're going to get 3e to the x minus 2, we okay? And I'm right using the other notation, g of f of x, that's kind of what maybe we're more familiar, a little more comfortable. I think you're more likely to see it written this way. G of f of x, we're going to plug all of the f of x in place of the x. So you get this e to the 3x minus 2, the composition of functions. So here I gave you the functions as equations, but we also want to be able to do it if I give you the functions as graphs. So let's look at, let's say we got 1, 2, 1, 2, 1, 1. And we're going to go, this is f of x, and then we'll go 1, 2, 1, 2, 1, 1, and we'll say that is going to be g of x. Okay. So we can ask, for example, what is f of g of 2? So I'm going to let you do that. I'll put another one down there for you too. Let's do g of f of 2. And for fun, let's do f of 2. So see if you can come up with those, and then we'll talk about them. Feel free to, yes, you can even talk to somebody that's close by. Compare answers. Arm wrestle, socially distanced if you don't agree. So I'm going to work my way through. The 2 is going to go into G. So we go to x equals 2. You run down to the function to this point, and G of 2 is the y value. So that is going to be -1. And we take -1 as the x value to the function f. Go to the curve and read its y value, and that is going to be -1. So we say f of g of 2 is -1. We turn around now, here we go f of 2, so we go to 2 on the x, and its y value is 0. And so then we take 0 as the x value to g, and plug it in and read off the y value as 1. Okay? Now we're going to do it twice into f. So 2 goes into f, and that becomes 0. And then 0 goes into f, and that's still 0. And so we get 0. Good to go? So we look at equations, we look at a function given as a graph, and so we'll also do it with the function given as a table. So numerically is the words they would use. So I'm going to say here's x and f of x. So the x values are going to be 0, 1, 2. And the y values are going to be 1, 3, 5. And I'm going to switch to g. And g is going to be, for x values, g is going to get 1, 2, 3. And its y values are going to be 2, 4, 6. And so we'll see if using those as our f and g, can we find f of g of 1? Can we do g of f of 1? And can we do f of 0? So finding our way through, we go to G and find 1. That's right here. We read off its y value, so that becomes f of 2. Then we take 2 over to the table for f, and that gives us 5. And so that's going to be f of g of 1 is 5. And here we take 1 to the x table, that's going to be 3. So we get g of 3. And 3 on g gives us 6, so g of f of 1 is 6. And we do f of 0, which gives us 1. And we go back to f and plug in 1, which gives us 3. Make sense? Okay. So I'm going to play a little game here where I'm going to give you a function, h of x, that is the composition of two functions, f and g, and you can try to find the f and g. So h of x is going to be equal to, we will say, the square root of 3x minus 2. And h of x is f of g of x. It's a composition of two functions. And can you find a possible f of x and g of x? Now, this is not unique, and you can be creative here if you choose to be so. And there's a couple of cheater ways that once you find the cheater way, then becomes disqualified for future problems. Found the cheater way already, Sam? Do you understand how the game is played? You may need an example. You may want to volunteer one, or do you want me to volunteer somebody? Eyes go down. Volunteer? How about a g of x? Anybody find a g of x? So, yeah, that's the natural choice. Yeah, because g of x is the inside function. And inside here is the 3x minus 2. That's kind of a natural choice. Then what is the outside function? What is g sitting inside of? Square root of x. And that's one possibility. Okay, anybody get real creative? Anybody get a little bit creative? Anybody out there have a pulse? Do you want to see the cheater ways, or do you even care? Oh, absolutely. If we can cheat, I want to know how. Let's see how that works. You could say g of x is x, but that's cheating. That's okay, because what does that make f of x? So that's banned from ever being used again. So, second, cheater method. G of x is square root of 3x minus 2. What does that make f of x? Boring. You may have something clever? I stalled to give you time. How disappointing. All that talent, and you're okay just coasting with it. Not going to push it at all. Seriously? Not one idea? Might have to make that a whole problem. All right, let's talk about odd and even. So this continues to come up in AP Calculus. So you just see it so irregularly that people really struggle to remember what it means. So if we say f of x, if f of x is even, then that means that f of negative x is f of x. F of negative x is equal to f of x. That's the definition of an even function. So geometrically, you can see that reflecting in the y-axis is exactly the same as the original. So a classic even function, once you remember, is one that has an even power, right? X to the second. And another trig function that's even. Testing. Is this on? Even function, trig function. You remember trig? Sines, cosines, tangents? Okay. Yeah, the cosine. Whew. Well, I was going to have to reteach all of AP Prep for a moment there, but no. Somebody knows it. So if you flip a cosine curve in the y-axis, it lands on itself. Cosine is even. Remember we said, I'm going to answer this question. Already broken my heart. Cosine of negative x is cosine of x. That's an even function. Yeah, now you know it. Okay, f of x is odd if f of negative x is negative f of x. So, classic example of an odd function is anything to an odd power. So if we say call f of x equal to x to the third, it has that property that when you reflect it in the y-axis, that's the same as if you reflect it in the x-axis. Or this is also called, so this is called also symmetry in the origin. So a double reflection takes you back to where you were, y-x, x, y. Or if you put your pencil on the origin and rotate it 180 degrees, you get back to the same one. And we say even functions have symmetry in the y-axis. Okay? So let me ask you an interesting question. I'll give you a point and ask you where there must be another point if the function is either odd or even. So we'll say here's a point, negative 32. So can you find a second point if A, f is even, or B, f is odd? Is that hard?
Blurt it out, or
Blurt it out. I would love that. What if it's even? What's another point on the graph?
3, 2.
Exactly. Because you got to have symmetry in the y-axis. So if you flip that, it's going to put you at 3, 2. That's exactly right. And somebody else, because they knows what's going on. How about if it's odd? What must also be a point there?
Would it be 3, negative 2?
Exactly right. And so you can do it one of two ways. You can imagine rotating it, which sometimes is hard, or you can double reflect. So it's going to put you at 3, negative 2. Or you can see that you're going to change the sign in both x and y. Nice. Okay. Let's up the game a little bit. So here's the original, or here's part of the original. And that's a piece of y equals f of x. So complete the graph. If A, f is even, and B, f is odd. So draw another part of the graph if it's even or odd. Okay, so with your finger in the air, show me the whole graph of f if f is even. Oh, looks like the Rocky Mountains, right? Got it. So there is the even part. Tougher. What's it going to look like if f is odd? Oh, you guys are good. Kind of like a pointy sine curve. Okay? All right, very good. You do remember something. So let's talk about inverse functions. So suppose we say y is equal to 2x cubed plus 1. Let's call f of x equals 2x cubed plus 1. Can you find F inverse of x. Anybody not remember how to start on that? We need a hint.
Like, you know, like that, so when it's x equals 2, 1, then
Good. And then we're going to solve for the y here. Okay, remember that? Very good. Can't believe I'm going to make it. Anybody not get here? Need help getting here? Okay, now a thinking question. What kind of functions have inverses that are functions? Understand the question? And maybe I should say, I didn't say this, the graph of a function that's inverse, how are they related to each other? So here's some famous inverses. F of x equals e to the x, and what does that make F inverse of x? What's the inverse of e to the x? Oh, great. Excellent, excellent, excellent. So, we graph them. With your finger in the air, show me what e to the x looks like. Ah, some of us know. Some are just waving. No, it looks like an exponential growth, right? There's e to the x. With your finger in the air, what does the natural log of x look like? Yeah. And what you notice, or hopefully you notice, is that they are reflections of each other in the line y equals x. Now, we started with a function e to the x. Its inverse is also a function, right? This passes the vertical line test, e to the x. So we can look at the graph and know that it's a function. We look at its inverse, it also passes the vertical line test, it's also a function. That's not always the case. There are functions whose inverses are not functions. What's an example?
x squared.
X squared. Very good. So if we did y equals x squared, if we tried to graph its inverse, we can. Show me with your finger in the air, what's the graph of its inverse look like? Oh, those are good. It's going to be a sideways parabola. So the original is a function, it passes the vertical line test. The inverse is not a function, it fails the vertical line test. What characteristic or quality does the function have to have in order to guarantee that its inverse is a function? Okay, true. And so what's the name of a function? Well, every function has an input that's only got one output. But what special kinds of functions? I think what you're saying is, actually, well, an odd function is going to have an inverse. That is true, that is a function. But there are other functions that aren't odd, right? E to the x is not odd, but it has an inverse that is a function. So there's something other difference behind that too.
Is it the horizontal line?
Yes, it must pass the horizontal line test. This is one way of saying that. Excellent. So you can see that e to the x not only does it pass the vertical line test to be a function, but it also passes the horizontal line test. So when you switch that x and y, the result, the inverse, is because this passed the horizontal line test, its inverse will then pass the vertical line test and be a function. What's another name for that if it passes the horizontal line test? Anybody remember? No, I guess would be the answer. It's a one-to-one function. Okay. There's another name we just learned. Oh, time one day to the next. Who would have thought? What kind of function is this when it is always increasing? It's exponential, but that's not any function, even if it's not exponential, that is always increasing. We gave a name for it. We just talked about it. Oh, who said that? That girl. Yes, and in fact, it is strictly monotonic. And I'm going to put in parentheses, always increasing or always decreasing. That's what we mean by strictly monotonic. Excellent, excellent, excellent. Well, guys, I don't know how, but we made it through an entire lesson in one class period. Amazing. So now hopefully you can do homework number 4.
That's for them.